Greetings. In the desperate final years of World War II, the Allies' industrial and technological might began to tilt the balance decisively in their favor, especially over Germany, where resource shortages and relentless losses threatened to break their defenses. But what if the seemingly simple could carry profound strategic weight? Imagine a fuel tank made from nothing more than laminated paper and resin, capable of extending a fighter's range by over 1,000 miles, yet so fragile that it could only be used once before jettisoning. How did the Americans manage to produce such lightweight, expendable tanks en masse, and what did this reveal about their industrial capacity? Could Germany's highly skilled engineers have ever foreseen that their adversaries would turn to paper, rather than metal, to solve a critical logistical challenge? And what does the discovery of these tanks, scattered across German fields, say about the true scale of Allied resourcefulness? All these facts point to one burning question. How did the Allies, with their overwhelming industrial strength, transform wartime logistics into a weapon as powerful as their aircraft and bombers? This video will trace how the development of these paper-drop tanks symbolized the broader victory of mass production and resourcefulness, showing how simple materials, when combined with innovative design and enormous manufacturing capacity, reshaped the air war over Europe and sealed Germany's fate. The story begins now. In March of the year 1944, at the Recklinlatz airfield nestled in the region of Mecklenburg, Germany, a critical phase in aerial intelligence was unfolding. The Luftwaffe's technical intelligence units had dedicated themselves increasingly to a meticulous analysis of captured enemy aircraft, an endeavor that had gained paramount importance amid the intensifying air war. At this period, within the walls of Air Probong Stella Rechlin, which served as the Luftwaffe's central hub for aircraft testing and evaluation, teams composed of expert engineers and seasoned pilots tirelessly endeavored to dissect every detail of the captured craft, seeking to uncover the strategic edges possessed by the Allied forces. Their investigations aimed to reveal how these aircraft achieved their operational success and what technological advantages they could exploit. The discoveries made in the early months of spring in 1944 would prove to be revolutionary, fundamentally shifting the German understanding of American industrial strength as well as shaping predictions about the future trajectory of the aerial combat over the Reich itself. The momentous event that sparked this new wave of intelligence occurred on the 6th of March. A well-preserved P-51 Mustang, an aircraft renowned for its speed, range, and maneuverability, arrived at Rechlin, having been moved by train from a crash site in the vicinity of Brandenburg. This particular aircraft had been shot down less than 2 days prior during a highly significant American fighter escort mission aimed at Berlin, marking a pivotal shift in aerial tactics. Unfortunately, the pilot had not survived the impact, but the aircraft itself remained in remarkably good condition, offering the German technical teams their clearest insight yet into a model that was rapidly but quietly changing the strategic landscape of air power over Germany. The first person to oversee the detailed examination was Man V. A. Bombeck, a veteran involved in aircraft development, who would later go on to command the Kampfgeschwaden unit. As the German engineers and analysts began their disassembly and analysis, they noted that the American pilots' navigation charts still lay in the cockpit, clearly showing the flight route from an airfield at Debden in England, through the airspace over Berlin, and back, an entire round-trip distance exceeding 1,000 miles. This served as an immediate indication that the aircraft's range and endurance capabilities might be greater than previously estimated. The technical evaluation commenced without delay. Prior to this, German intelligence had been monitoring reports indicating increased American fighter activity deep within German-held territory. However, the prevailing official interpretation was that single-engine fighters, due to their limited fuel capacity, lacked the endurance needed to reach and effectively escort bombers all the way to Berlin and back. The typical distance from British bases to the German capital was approximately 560 miles one way, a span that historically had presented significant logistical challenges. Previous assessments, founded on the analysis of captured aircraft such as the P-47 Thunderbolt and the P-38 Lightning, had concluded that these fighters, even when equipped with additional external fuel tanks, could not reliably maintain combat operations over such a lengthy range. They had demonstrated only limited penetration into German airspace before fuel constraints compelled a return to base, an understanding that had shaped German defensive strategies and countermeasures. However, the events of the early March days shattered these long-held assumptions. On March 4, American P-51 Mustangs belonging to the 4th Fighter Group, recently transitioned from flying P-47s, had participated in their maiden escort mission over Germany with their new aircraft. The mission was initially limited, involving a small bomber force heading toward Berlin, and hampered by weather and communication issues, resulting in less than half the intended number of bombers reaching the target. Despite this, the significance was unmistakable. For the first time, American single-engine fighters had reached Berlin, engaged in combat, and successfully returned to England. Just 2 days later, the 6th of March, marked perhaps an even more notable event. A massive daylight raid involving over 660 bombers, which targeted Berlin directly. These were accompanied by more than 150 P-51 Mustangs, P-38 Lightnings, and P-47 Thunderbolts serving as escorts. During this daylight offensive, the escort fighters not only fought Luftwaffe interceptors over the skies of the German capital but also successfully escorted the bombers back home, engaging in combat and maintaining formation throughout the mission. The occurrence of such an operation was no coincidence. It was a clear indication that the American forces had overcome previous limitations. The result was a breakthrough in escort fighter capability, that ongoing technical problem which had plagued Allied air operations for months. It became evident that the Americans had indeed solved the puzzle of long-range escorting. The implications of this shift rippled through Luftwaffe's strategic planning. Notably, this was not a fleeting success, nor was it a mere fluke. It represented a new era, an era in which the American airpower could project strength deep into German airspace, with fighters reaching targets previously considered beyond their reach. The discovery of the nearly intact Mustang aircraft and the insights gleaned from its Colonel de Jagdflieger, renowned as one of Germany's most accomplished fighter aces with a tally exceeding 100 aerial victories, had managed to continue flying combat missions even during his administrative duties. His keen eye had repeatedly encountered formations of P-51 Mustangs over the skies of Germany, a sight that immediately set off alarm bells within him due to the implications it carried for the ongoing air war. His first-hand experience and tactical awareness prompted him to recognize that these American fighters presented a formidable challenge, especially given the seemingly unexpected endurance and reach they had demonstrated. In his official combat assessments submitted through the proper channels, de Jagdflieger observed that American P-51 fighters operated at full combat capability over Berlin, engaging aggressively and without any visible attempt at fuel conservation. Unlike what many might have suspected, these fighters were not merely spraying and praying or flying at the edge of their range limit. Instead, they appeared to possess significant reserves of fuel, enabling them to sustain prolonged combat engagements with relative ease. This revelation struck directly against the preconceived notions held by Luftwaffe intelligence. Gallen's reports underscored the P-51's exceptional high-altitude performance, where the aircraft outperformed both the Messerschmitt Bf 109 and the Focke-Wulf FW 190 in terms of speed and maneuverability above 20,000 feet. These findings highlighted the aircraft's true potential in combat, especially in the high-altitude environment typical of engagements over Berlin. With such capabilities, the critical question arose: how exactly had the Americans managed to extend the range of the Mustang so significantly? Efforts by the technical evaluation team focused on dissecting the design and fuel capacity of the P-51B model, an iteration known for its improved range. They began by carefully measuring its internal fuel tanks. The aircraft was equipped with two wing tanks, each capable of holding 92 gallons of aviation fuel, summing up to a total of 184 gallons stored within the wings. In addition, a notable feature of the P-51B was its fuselage tank, an 85-gallon unit positioned just behind the cockpit, added during production to further extend its operational range. This fuselage tank was a relatively recent addition to the series, specifically engineered to provide the Mustang with extended endurance. When all tanks, wing and fuselage, were combined, the internal fuel capacity reached a total of approximately 269 gallons. The heart of the aircraft's high-altitude performance lay in its power plant, the Packard Merlin engine, a licensed version of the famous Rolls-Royce Merlin. This engine had revolutionized the Mustang's capabilities, especially at high altitudes, and consumed fuel at varying rates depending on the power settings used during flight. Typical fuel consumption rates helped to clarify the aircraft's endurance. At low, economy cruise settings, the Merlin engine burned roughly 60 gallons of fuel per hour. At a more moderate, normal cruise power, consumption increased to about 75 gallons per hour. Using these numbers, German engineers performed their calculations to determine the range limits of the aircraft when operating under typical combat conditions. Considering the total internal fuel capacity of approximately 269 gallons and an average cruise consumption of roughly 70 gallons an hour, the P-51B could sustain flight for about 3 hours and 58 minutes. Given its cruising speed of around 300 miles per hour, this translated into a maximum theoretical range near 1,140 miles. What was critical about this figure was that it was just enough for the Mustang to reach and fly around Berlin from bases in England and return home, a feat that was narrow but achievable, and notably without reserves for combat or emergency scenarios. However, operational and combat reports painted a different picture. American fighters frequently engaged in extended dogfights over Berlin, sometimes lasting 15 to 20 minutes before breaking off. Such intense combat would have consumed fuel at rates exceeding 100 gallons per hour, far above normal cruising conditions. Under these circumstances, aircrews reported running dangerously low on fuel, with many having to break off combat early or risk being stranded, yet they still managed to fly back to base. This discrepancy begged an important question. How could the Germans account for the observed combat endurance and range? The answer lay in a detailed examination of the aircraft's structure, particularly its wing configuration. The technical staff took a closer look at the wing assemblies and noticed something significant. The P-51B was equipped with standardized hard points beneath each wing designed explicitly to carry external stores. These hard points were interconnected with fuel line connections, indicating that they could accommodate external fuel tanks specifically designed to enhance range. Use of external fuel tanks, often called drop tanks, was not a novel concept for the Germans. Their fighters had employed similar auxiliary tanks since the earlier days of the war. Such tanks could be mounted externally and jettisoned when empty, effectively extending the aircraft's fuel capacity and operational reach. The realization was that the American P-51s, even if equipped with standard internal tanks, could further augment their range through the attachment. In the modern history of aerial combat, European air forces extensively used military aircraft equipped for extended-range missions, and among these, the German Luftwaffe stood out for its strategic emphasis on such capabilities. The formidable Messerschmitt Bf 109, a mainstay of Germany's fighter fleet, was capable of carrying a supplemental drop tank with a volume of 300 liters, a design choice that significantly extended its operational reach. The more versatile Focke-Wulf FW 190 routinely employed these external fuel tanks to facilitate longer reconnaissance or escort missions. Drop tanks played a critical role in wartime aviation, as they allowed aircraft to carry additional fuel externally without sacrificing underlying performance. Before entering combat zones, pilots could jettison these tanks, discarding what was no longer needed, to minimize drag and weight, ultimately enhancing agility and speed. This maneuver was a common tactic across all aviation forces involved in the conflict. It was not merely a question of whether these tanks were in use, but more about understanding their size, capacity, and the extent to which the United States' manufacturing capabilities could sustain the production of such fuel extensions at a rate fast enough to uphold consistent, operationally demanding missions. Following reconnaissance missions, especially those conducted in March, Allied intelligence teams immediately initiated efforts to locate American-made drop tanks, hypothesizing that their design and capacity might reveal critical insights into U.S. industrial output and logistical planning. To achieve this, intelligence officers meticulously analyzed reports from Luftwaffe pilots to identify probable points where enemy aircraft might jettison their external stores, typically upon encountering enemy fighters. It was understood that external tanks often compromised aircraft maneuverability and velocity, prompting pilots to release them at strategic moments during combat engagements. In the weeks that followed, reconnaissance and local search teams, comprising Wehrmacht personnel and youthful volunteers from the Hitlerjugend, spread out across the countryside northeast of Berlin in an organized attempt to recover debris from fallen aircraft. Their task was both tactical and intelligence gathering, as the wreckage could unravel critical technological details. Within just 3 days, they successfully recovered numerous fragments strewn across open fields and wooded areas in the region. Most of these pieces were damaged or fragmented due to high-impact crashes, crushed on collision or battered by their descent through the atmosphere. Nevertheless, 2 notably well-preserved tanks landed in softer terrain, such as in fields of winter wheat, where the soft soil absorbed much of the impact, conserving their structural integrity sufficiently for detailed examination. These captured drop tanks soon revolutionized the German understanding of American aircraft technology and manufacturing techniques. The tanks were cylindrical, approximately 108 inches in length and roughly 22 inches in diameter at the broadest section. Calculations and measurements from the recovered tanks indicated that each could hold around 108 U.S. gallons, or approximately 400 liters, of fuel. To put this in perspective, 2 such tanks, when mounted, would add approximately 216 gallons of fuel capacity to the aircraft's onboard reserves. This significant increase dramatically extended the operational range of fighter planes such as the P-51 Mustang, boosting their total fuel capacity to nearly 485 gallons. With this augmented fuel load, a Mustang could sustain flights for around 6.7 hours, calculated at cruising power settings, thus offering a range that exceeded 2,000 miles. Such endurance was more than adequate for missions targeting Berlin, providing the fighters with a substantial operational buffer and the ability to perform deep penetration strikes while maintaining tough combat reserves. The detailed mathematics behind the fuel capacity now made perfect sense to the German engineers, but what immediately captured their attention was not just the volume each tank could carry, but rather the ingenuity of their construction. When examined closely, they discovered that these external drop tanks were not simply fabricated from typical metals such as aluminum or steel, as was common in aircraft design, but composed of surprising and unconventional materials. A careful tactile inspection of the tank's surface revealed that it was covered with a textured layer unlike any standard aircraft alloy. The characteristic shine and slickness of metal surfaces were absent beneath the coating of silver paint. It was clear that the fundamental material was something else entirely. When researchers scraped away a small section of this paint, the true composition became apparent. They found multiple layers of a heavy-duty paper, each approximately half a millimeter thick, carefully compressed and laminated together using a resilient adhesive. This layered paper construction was both sophisticated and highly deliberate in its design. The nose and tail cones of the tanks were formed by overlapping sheets of this material, pressed into shape similarly to traditional papier-mâché but on a more advanced industrial scale. These overlapping pieces created visible ridges, giving the surface a scalloped appearance that evidenced the meticulous way each segment was fitted together. The central section of the tank was seamless, a continuous wrap around a cylindrical form, with layers laid down in a uniform, spiral manner. The fuel fittings, fabricated from brass, were precisely machined and sealed with meticulous care to prevent leaks, demonstrating the advanced engineering skills employed. When peering through the layers, researchers observed the reveal of the filler cap brought to light an intriguing discovery. The interior surface of the tank had been coated with what appeared to be a cellulose-based lacquer. This specialized coating was specifically designed to withstand the highly corrosive nature of aviation gasoline, which, in the context of wartime operations, posed a significant threat to standard materials. In the wake of this finding, the experts from Germany specializing in advanced materials were swiftly brought in to conduct a thorough examination of the tank's construction. Their detailed analysis uncovered that the core material of the tank was crafted from high-quality craft paper. This particular paper was produced through a chemical pulping process, which significantly enhanced the strength and durability of the cellulose fibers embedded within it. Such fibers, and the paper itself, were known for their exceptional resilience and were commonly utilized in the manufacturing of heavy-duty shipping containers and advanced industrial packaging, highlighting the robustness of the material. Further scrutiny of the bonding agent used in the construction revealed that it was a formaldehyde resorcinol resin, a thermosetting polymer that, when cured with heat, formed bonds that exceeded the strength of the paper fibers themselves. The lamination process employed a series of at least 12 distinct layers of this specialized paper, each carefully oriented in different directions. This deliberate layering strategy was essential to ensure the tank's structural integrity in multiple planes, effectively distributing stress and resisting pressure from the contained fuel. Within the tank, wooden anti-slush baffles had been installed. These components served a vital function, preventing the fuel from sloshing excessively during maneuvers, which could impair the aircraft's stability and handling. The inclusion of wooden baffling subtly hinted at resourcefulness, utilizing readily available materials to optimize performance under combat conditions. What became immediately apparent was that the entire manufacturing process had been designed with standardization and mass production in mind. Despite the unconventional material choice, the finished, empty paper tank weighed about 80 pounds. This compared favorably to a traditional metal tank of similar or smaller capacity, which typically weighed between 65 and 75 pounds. While the paper construction was not necessarily lighter than its metallic counterparts, it offered critical advantages, particularly in the context of wartime resource management. The implications of this innovation did not escape the attention of the technical team at WWII. It quickly became evident that the United States had developed a technique to produce fuel tanks from non-strategic raw materials, components that did not rely on scarce metals like aluminum or steel, both of which were increasingly difficult to procure during wartime shortages. The entire manufacturing process required no specialized metalworking equipment, no welding, no sheet metal forming, and could be carried out without the need for highly skilled metal craftsmen. Instead, the tanks could be manufactured in facilities equipped to handle paper and wood-based products, a category covering hundreds of factories across the nation. In practical terms, even converting a modest fraction of America's extensive paper industry capacity into drop tank production could result in a substantial output. If just 1% of the nation's annual paper production, totaling roughly 12 million tons before the war, was redirected to wartime manufacturing, this could yield well over 100,000 tanks each month. Such an output far exceeded any strategic need for P-51 fighter operations or similar aircraft support, rendering these tanks an effective resource surplus. Moreover, the absence of manufacturing marks, serial numbers, or any identifying symbols suggested that these paper tanks were mass-produced commodities, potentially meant for complete expendability after a single use. Their design was simplicity itself but highly effective, emphasizing rapid production and disposability as key features. Investigations into the American paper industry capacity confirmed these suspicions. The scale of output was staggering. The United States' vast and versatile paper industry could be leveraged extensively. The real limiting factor in producing such tanks would not be the materials themselves but the availability of manufacturing facilities and labor. Fortunately, the assembly process posed little challenge. It required only minimal training for semi-skilled workers to produce these tanks rapidly. This approach epitomized industrial efficiency and resourcefulness, showcasing how wartime industries could innovate with existing materials, turning routine paper and wood-based resins into critical military assets. German analysts viewed this development with a mixture of astonishment and concern, as it represented a level of manufacturing ingenuity that was remarkably difficult to counter. Further analysis of the tank's design clarified that they were strictly meant for single-use scenarios. These tanks would be installed into aircraft, used until depleted, and then discarded, aligning with the overarching strategy of mass production and rapid deployment amid the pressing demands of war. During the intense period of World War II, one of the most crucial aspects of successful aerial combat involved the development and utilization of fuel tanks that could keep pace with the demanding operational requirements of modern fighter aircraft. Among these innovations was the approach to creating lightweight, efficient, and quickly deployable drop tanks, which significantly enhanced the range and operational flexibility of fighters on both sides of the conflict. The materials employed in fabricating these tanks played a pivotal role in their effectiveness and logistical efficiency. A particular type of adhesive, derived from resources expensive and in limited supply, was used to assemble the tanks. This adhesive, designed to form robust, strong bonds once cured, had a notable drawback. It was gradually dissolved when subjected to continuous exposure to aviation gasoline. This meant that although the bonds were initially secure enough for flight, their integrity could weaken over time if the tanks remained filled with fuel for too long, especially under conditions of prolonged contact with the gasoline used by aircraft engines. Intelligence agencies, through various reports and the interrogation of captured American airmen, confirmed that these paper-fabricated tanks, often referred to as paper drop tanks, had to be filled just before a sortie. They could not be stored in a filled state for multiple hours without risking leaks, as the prolonged contact with the fuel would compromise the adhesive bonds and, consequently, the tank's integrity. Despite this apparent limitation, it did not impose significant operational restrictions. In practice, fighters would be fueled during pre-flight preparations, a routine thought to be manageable within the framework of combat logistics. Once filled, the tanks were intended for short-duration use, generally only benefiting the aircraft during the actual mission. After their primary purpose was fulfilled, these tanks would be jettisoned, discarded in flight to reduce weight and streamline the aircraft's profile for combat engagement or return. This single-use approach simplified logistical procedures considerably, eliminating the necessity for recovery, cleaning, inspection, or maintenance. The design intentionally favored expendability, allowing for quick deployment and discard, which enhanced aircraft performance and operational tempo. An additional feature of the design was the distinct color coding used by the manufacturing authorities. The paper-made tanks were painted silver, a choice driven partly by the need to reflect solar heat and thus reduce internal fuel vaporization, an important consideration at high altitudes where intense sunlight could cause rapid evaporation. Conversely, the standard metal tanks used by American forces were painted gray, helping ground crews rapidly identify tank types during refueling and servicing operations. This quick visual differentiation was essential for managing large quantities of modular components efficiently in the midst of combat conditions. Every facet of these tanks' design reflected an orchestrated effort toward engineering optimization for mass production and field deployment. By late March of the year 1944, German intelligence managed to trace the origins of these innovative paper drop tanks back across the Atlantic to British development efforts. It was discovered that the British Air Ministry, recognizing the strategic importance of conserving scarce metals, particularly aluminum, had initiated a project to develop fuel tanks made from impregnated paper during the year 1943. The task of bringing this concept to fruition was entrusted to the Bowater-Scott Corporation, a company with renowned expertise in manufacturing paper-based products. They crafted a specialized production process capable of turning raw materials into durable, lightweight fuel tanks suitable for aerial use. These paper tanks began entering service with Royal Air Force fighter squadrons towards the end of 1943. Their success prompted rapid adoption by American forces, who, leveraging their extensive industrial capacity, produced the tanks through multiple manufacturers, both in Britain and the United States, for use across various fighter groups of the U.S. Army Air Forces. This innovation, initially driven by British resource scarcity, acquired new significance through American industrial might, leading to its deployment on a potentially massive scale. The implications stretched well beyond the simple construction of fuel tanks. Furthermore, German technical personnel undertook a systematic review of captured American equipment, seeking out other examples of industrial ingenuity and mass manufacturing techniques. The thorough investigations revealed a recurring theme. Although American technology in certain areas, such as optics, small arms, and armor metallurgy, sometimes surpassed their German counterparts, the true strength of the American approach lay not solely in individual component quality. Instead, it was evident that American equipment was generally better manufactured, characterized by broader standardization, higher reliability, and availability in far greater quantities than comparable German systems. The key to this success lay in the American philosophy of prioritizing manufacturability over perfection. Components were deliberately designed from the outset for mass production using semi-skilled labor and standardized tooling. The principle of interchangeability played a critical role, ensuring parts could be swapped and assembled in any unit without the need for custom fitting. Assembly lines, inspired by efficient industrial practices, enabled rapid production, drastically reducing manufacturing times while significantly increasing output capacity. This contrast starkly highlighted the differences between the American and German production philosophies, where German manufacturing often focused on meticulous craftsmanship and specialized components. American methods emphasized quantity, repeatability, and rapid deployment. The results significantly influenced the overall war effort, contributing to the Allies' material advantage and systematic during World War II. German military hardware consistently stood out as a testament to engineering excellence. Their weapons and equipment often reflected meticulous craftsmanship, with each piece precisely handcrafted by highly skilled artisans. For instance, a German tank or aircraft engine represented the pinnacle of technological refinement, embodying superior precision engineering and meticulous attention to detail. However, this level of craftsmanship demanded a considerable investment in skilled labor, specialized tools, and extensive time for each unit's production. Consequently, the rate at which such advanced equipment could be manufactured was inherently limited by the availability of master craftsmen and the specialized manufacturing machinery required. This meant that although Germany could produce highly sophisticated individual items, the overall volume was constrained by these factors. In contrast, the United States focused on mass production, creating products that, while perhaps not always as refined as their German counterparts, were available in vast quantities and met operational needs effectively. Their strategy was rooted in the principle that, especially in the chaos of modern industrial warfare, sheer volume could often outmatch the finest craftsmanship in the long run. This approach proved decisive in the fulfillment of wartime material demands. A compelling illustration of this principle can be seen in the production of the P-51 Mustang, one of the most iconic aircraft of the war. The original design of the Mustang, officially designated the NA-73X, was developed swiftly in response to a British requirement in the year of 1940. Remarkably, North American Aviation completed the prototype only 117 days after securing the initial contract, setting a record for rapid development in aviation history. The first successful flight of this prototype took place on October 26, also in 1940. The speed of the design-to-flight process underscored North American aviation's innovative approach to aircraft manufacturing. By 1944, North American had established two primary factories dedicated to building the P-51 Mustang. One was located in Englewood, California, where the plant at its production peak made approximately 364 aircraft each month. The second was situated in Dallas, Texas, contributing additional output. When both plants operated at maximum capacity throughout the year, combined production averaged around 574 Mustangs every month, with the pace accelerating as the war progressed. During the laying of 1945, the most ambitious month saw the production of up to 881 aircraft, more than double the monthly average early in the cycle. Each P-51 Mustang was composed of roughly 15,000 distinct parts, manufactured by hundreds of subcontractors located across the United States. The engine for the Mustang, the renowned Merlin produced by Packard in Detroit, was also manufactured at high rates, exceeding 300 units each month. Final assembly of a P-51D aircraft was an intense operation, requiring approximately 22,000 man-hours of labor. However, due to the efficiency of modern assembly lines, completed aircraft emerged rapidly, with a new Mustang rolling out of the factory roughly every 2 hours at peak efficiency. This scale and speed of production vastly surpassed contemporary German efforts. In early 1944, the combined German production of fighters by Messerschmitt and Focke-Wulf was around 600 aircraft per month, a quantity that German industry could only match through emergency priority measures and forced labor, rather than through sustainable or efficient manufacturing practices. Resource-wise, the United States held a decisive advantage in materials necessary for aircraft production. In 1944 alone, American aluminum production soared to approximately 1,250,000 tons annually, equivalent to about £2,500,000,000, and marked a significant increase from the pre-war output of around 164,000 tons in 1939. Conversely, Germany's aluminum production peaked at roughly 250,000 tons yearly and was on the decline due to bombings targeting its facilities and the loss of critical bauxite sources needed for metal extraction. The Americans possessed roughly 10 times the aluminum production capacity of Germany, ensuring they could meet and exceed the raw material demands of their manufacturing needs. Interestingly, despite the availability of sufficient aluminum to produce every drop tank in metal, American manufacturers opted for paper instead of metal for these auxiliary fuel tanks. The decision was driven not by shortages but by economic factors. Paper was cheaper, required less critical processing, and could be produced more rapidly and in larger quantities. This choice exemplified the American approach of maximizing efficiency and resourcefulness, enabling them to produce in large volumes while conserving strategic materials for more critical components of their aircraft and vehicles. German aircraft manufacturing facilities, once capable of mass-producing new planes efficiently, began to see a remarkable shift in their production methods, largely due to innovative strategies aimed at conserving resources and accelerating output. Instead of relying solely on the traditional, labor-intensive manufacturing processes, they repurposed existing aluminum supplies that could now be redirected toward other crucial military needs. This realignment allowed for the rapid construction of aircraft with fewer skilled workers, significantly streamlining the process and increasing the overall number of fighters and bombers that could be deployed in the theater of war. Such measures were driven not by desperation, but by a calculated effort to optimize resources and manufacturing capacity amid intensifying pressures on the Luftwaffe's operational effectiveness. The psychological and strategic impact of these developments quickly rippled through the ranks of the German Air Force, known in their own tongue as the Luftwaffe. Widespread awareness of these technological and logistical improvements undermined morale and confidence, especially when the contrast with Allied capabilities became stark. A particularly telling symbol of this newfound technological edge was the so-called paper drop tank, an innovative, lightweight auxiliary fuel container that exemplified the kind of resourcefulness that characterized Allied industrial effort. These drop tanks, often manufactured from readily available materials, became not just functional equipment but also potent visual symbols of American industrial prowess and the systemic disparity in resource availability between the Allies and the Axis powers. In the German military's strategic briefings, captured examples of these tanks were openly displayed for Luftwaffe personnel. Pilots, especially those transitioning from training schools into operational fighter units, were shown firsthand these advancements and then tasked with assessing their tactical significance. They were asked to determine the implications for combat strategy. The underlying message being conveyed was unambiguous. American fighters, now equipped with extended-range drop tanks, could provide escort for bombers anywhere within German airspace. Previously, the German defensive approach depended heavily on a strategy of engagement with Allied fighters only after the bombers' fuel supplies were nearly exhausted, which often meant waiting at a safe distance and then turning back. This advantage was now nullified because German fighters would need to confront the increasingly capable escort fighters early in the mission, inevitably resulting in costly aerial battles. Throughout the spring of 2044, the Luftwaffe's leading operational officers, including the legendary General Adolf Galland, provided their assessments in high-level meetings. Galland repeatedly emphasized a vital military reality. The American P-51 Mustang had emerged as the superior fighter above 20,000 feet. Its remarkable speed at altitude surpassed that of the German Messerschmitt Bf 109, while its maneuverability outperformed that of the Focke-Wulf FW 190. These characteristics, combined with the extended flight range granted by the revolutionary drop tanks, meant that Allied fighters could now accompany bombers throughout their entire mission profile, covering the entire flight from England, deep into German-controlled territory, and back. No longer could the Luftwaffe planes attack unmolested during bomber formations without facing fierce opposition. Every interception now entailed fighting through high-density fighter screens with significantly increased risks. As a result, German fighter losses surged at an alarming rate. The collection of aerial combat data from January 2044 revealed that roughly 90 Luftwaffe fighters had been destroyed, even as they claimed to have downed nearly 150 Allied aircraft. By February, these figures worsened. Approximately 160 German fighters fell in battle during that month, while Allied losses climbed to about 230 aircraft. The pattern was unmistakable. Losses were mounting so rapidly that they rapidly became unsustainable. The relentless efficiency of Allied air power meant that the United States and Great Britain could recover from their operational losses faster than Germany could inflict them. The summer months of 2044 marked the full blades of American escort fighter capability coming into sharp focus. The 8th Air Force, a formidable arm of the United States Army Air Forces, launched nearly daily deep penetration bombing missions over Germany when weather conditions permitted. Constant aerial protection was provided by the formidable P-51 Mustangs, which flew escort routes extending from England across the entire breadth of German territory and back again. The mounting losses suffered by the Luftwaffe fighters were catastrophic, placing huge strains on German military aeronautical resources. By June, the German defenses had already paid a heavy toll, losing in excess of 350 single-engine fighters merely in their efforts to defend the Reich during daytime operations. The subsequent month, July, saw crashes and losses that surpassed these figures, as more than 350 fighters succumbed, an attrition rate of roughly 31.2% each month. August proved similarly deadly, with losses reaching around 36%. With such relentless attrition, experienced German pilots were being killed or incapacitated faster than new pilots could be trained and brought into combat. Newly trained replacements typically amassed only about 150 hours of flying experience compared to the more seasoned American pilots, who often boasted at least 300 hours or more. Many of these replacements throughout this period, Dr. Galland consistently submitted detailed assessments to Hitler and the senior leadership of the Wehrmacht, providing stark evaluations of Germany's military situation. One such report, crafted in September of 1944, delivered its message with unflinching clarity. The Luftwaffe was no longer capable of winning the aerial war. The reasons were multiple and dire. Germany simply lacked sufficient resources. It was devoid of enough fuel supplies, enough aircraft, and most critically, enough trained pilots to challenge the overwhelming air superiority held by the Allied forces. The American Air Forces, backed by a vast industrial infrastructure, could replace aircraft and losses far more rapidly than Germany could manufacture new planes or recover from attrition. This disparity stemmed from the industrial and logistical gaps between the two nations. While the United States could churn out new aircraft and equipment at a relentless pace, Germany's industrial capacity was overwhelmed and unable to match this tempo of production. Their economy was stretched thin, strained by continuous demands for critical war materiel. The only remaining strategic option was to conserve what few resources remained, focusing solely on defending vital targets, and to cling to the hope that some form of political settlement might be reached before the Reich succumbed entirely to collapse. Throughout late 1944 and into the following year, Germany continued to experience an ongoing influx of supplies in the form of paper drop tanks, which fell en masse from Allied aircraft across Germany. German civilians quickly learned to identify these falling objects, which were often cylindrical, metallic-looking tanks with a silver sheen, lying scattered across fields, forests, and open land. Initially, many of them were alarmed, mistaking these routine aircraft deliveries for unexploded bombs. An error that caused widespread panic until military authorities reassured the population that these objects were harmless fuel tanks. Special instructions were distributed via civil defense organizations, emphasizing that these falling silver cylinders contained only empty fuel and were not weapons or explosives. The psychological toll of this aerial traffic was notably significant, as reflected in civilian morale assessments. Witnessing vast numbers of enemy aircraft overhead, their contrails crisscrossing the sky, and observing how nonchalantly these aircraft discarded empty fuel tanks, only reinforced the perception that the Allies possessed an abundance of resources. So abundant, in fact, that they could afford to waste fuel tanks in midair. To the beleaguered German populace, this spectacle starkly symbolized the imbalance of resources. While Germany struggled desperately to conserve every drop of fuel and every piece of aluminum, the Allies seemed to operate with outright abandon, possessing more than enough to sustain their aerial campaign. Meanwhile, German intelligence agencies persisted in analyzing the captured American equipment collected throughout 1944. Early efforts aimed at understanding American technological capabilities evolved over time to focus on quantifying the extent of the industrial gap, a measure of how far behind Germany was in production and resource allocation. The question arose: could Germany manufacture similar paper drop tanks, the so-called drop tanks, of the Allies? From a technical standpoint, the answer was yes. Germany's chemical industry was well capable of producing the kinds of resins needed to create such tanks, and their paper mills could manufacture kraft paper suitable for this purpose. The manufacturing process was relatively simple and did not require highly sophisticated technology. Yet, despite this theoretical feasibility, the practical reality was quite different. Germany's chemical industry was operating at maximum capacity, producing synthetic rubber, explosives, and essential wartime materials, leaving no spare production capacity for non-critical items like drop tanks made of paper. The resins, while technically easy to produce, could not be diverted from vital wartime tasks, especially given the industry's full engagement in supporting the ongoing war effort. Furthermore, the German paper industry was fully committed to fulfilling military demands, primarily manufacturing maps, official documents, and packaging for ammunition and other supplies. More critically, there was no operational requirement within the Luftwaffe or Wehrmacht that called for extended-range drop tanks. By late 1944, Germany was confronting a severe fuel shortage, which was grounding a significant portion of its fighter aircraft fleet. Pilot training had been reduced to a bare minimum, and operational sorties were heavily limited by fuel availability, not the aircraft themselves. It was rendered pointless to develop or even consider the deployment of drop tanks designed to extend the fighter's range when, at the same time, the very fuel needed to sustain flight was scarce and dwindling. The irony of the situation was both sharp and bitter for German strategists. Just as the Allies had come up with a practical solution to extend their fighters' operational range using paper fuel tanks, fueled by the abundant resources of the United States, German fighters faced grounding and attrition due to a shortage of fuel supplies, which had already curtailed their ability to operate effectively. This was a stark illustration of contrasting industrial capabilities. The Americans, with their enormous industrial base, could resolve logistical issues with relative ease, producing excess supplies and innovations, even paper drop tanks, while the Germans, crippled by resource shortages, were unable to adapt their existing aircraft to extend range in the relentless progression of the Second World War. The mounting need for advanced aircraft capabilities demanded vast resources, more fuel, additional pilots, and greater quantities of aluminum for constructing aircraft frames. An increased industrial capacity was crucial, with enough surplus production to facilitate innovations such as paper drop tanks, an ingenious solution to extend the operational range of fighters. This was a formidable feat, requiring not only the raw materials but also an efficient logistical framework capable of rapid manufacturing and deployment. Contrasting sharply with Germany's military predicament, the Allied forces fought a war driven by abundance. Their industrial machine, unhampered by shortages, was able to produce aircraft and equipment on an unprecedented scale. They had the capacity to explore and implement innovative tactics, including the use of these paper drop tanks, their design and deployment enhancing the effectiveness of long-range missions. Meanwhile, Germany was embroiled in a war of profound scarcity, battling against an enemy for whom lack of resources was no insurmountable obstacle. Their industrial infrastructure was increasingly strained, struggling to match the relentless demand for aircraft, fuel, and trained personnel necessary to sustain operations against their formidable adversaries. By the month of January in the year 1945, the outcome of the conflict had become an unquestionable certainty. Soviet forces advanced relentlessly from the east, nearing the Uda River, which lay less than 50 miles from Berlin, the capital of Germany. On the Western Front, Allied forces had recovered from the setbacks of the Ardennes offensive and were pushing steadily toward the Rhine River, aiming to breach Germany's western defenses. The German Luftwaffe, once a dominant aerial force in Europe, was now largely reduced to sporadic efforts. Their limited resistance was hampered by dwindling fuel supplies and the heavy losses inflicted upon pilots, which further diminished their operational capacity. Within this environment of inevitable defeat, detailed and systematic studies of American military equipment continued, carried out at the research facility in Reikland. However, by this late stage of the war, such analyses had become more academic than strategic. Findings were meticulously documented for historical record but no longer possessed the power to alter the course of the conflict. Of particular significance was the comprehensive report finalized in late January 1945, focusing on the P-51 Mustang fighter and its innovative use of drop tanks. This detailed analysis cataloged every technical aspect of the P-51's range-extending capabilities, the construction of the drop tanks, the materials used, primarily non-strategic, readily available substances, and the projected production estimates. It also assessed operational implications for reinforcements and tactics. The report's conclusion was unequivocal. The combination of the P-51 Mustang equipped with these lightweight, disposable paper drop tanks had effectively rendered the German heartland indefensible against relentless American daylight bombing campaigns. The report vividly confirmed the dire reality facing Germany. They lacked the industrial capacity necessary to sustain American fighter production at the scale required. They did not have enough fuel to support prolonged and large-scale aerial operations, nor were they able to replace pilot losses quickly enough due to insufficient trained personnel. This technical and logistical shortfall was dramatically illustrated in the final analysis, which was stored away in the archives of the Reich Air Ministry by the end of January in 1945. Whether senior German military and political leadership actually read or understood this documentation remains uncertain. By that point, the existence of detailed technical reports analyzing American capacities was almost beside the point. The battlefield demonstrations had already made such conclusions clear. By early 1945, the Luftwaffe, which had once dominated European skies in 1940 in the Battle of Britain, was reduced to a ragtag force making occasional, desperate sorties. These missions were often constrained by fuel shortages and limited pilot availability, restricted to attempting frail raids that no longer threatened the strategic situation but merely served as heroic gestures of defiance. American fighters now roamed freely over German territory, confidently attacking targets of opportunity, escorting their bombers, and maintaining complete air supremacy over the region. Each paper drop tank falling from these American aircraft served as a tangible symbol of the immense industrial disparity that had, in the end, decided the air war's outcome. This disparity had been plainly evident during the June 1944 exhibition held in Reikland, where captured Allied aircraft were displayed before Luftwaffe personnel. Among these displayed aircraft were multiple examples of the P-51 Mustang, in addition to B-17 and B-24 bombers, P-38 Lightning fighters, Lancaster bombers, Mosquito fighter bombers, Typhoon fighters, and various models of Spitfires. Thousands of Luftwaffe pilots and ground crew members toured this exhibition, gaining first-hand experience with the enemy's advanced equipment. The prominently displayed paper drop tanks, accompanied by detailed technical diagrams, explained their construction, materials, and operational range enhancements. The exhibit served a dual purpose. It was both an educational platform for understanding Allied technology and a sobering reminder of the staggering industrial capacity that the Allies had assembled. The scale of Allied manufacturing, their ability to standardize components, produce vast quantities quickly, and innovate rapidly, the concept of operational effectiveness was vividly demonstrated through tangible, real-world examples of the aircraft equipment encountered daily in combat scenarios. Among these, the Kampfgeschwader 200, a specialized unit within the Luftwaffe tasked with conducting clandestine operations, including the perilous task of flying captured Allied aircraft, played a significant role in understanding and countering Allied tactics. Throughout the year 1944, this unit operated several P-51 Mustangs, utilizing them not just in missions but as valuable tools for evaluation and experimentation. These aircraft served as moving laboratories for Luftwaffe test pilots, providing them with direct, hands-on experience of the Mustang's performance attributes, an experience crucial for developing effective tactics against this formidable enemy fighter. Steady reports from pilots of Kampfgeschwader 200 consistently highlighted several key characteristics. Notably, the excellent visibility from the cockpit, which was particularly improved in the later model of the P-51, designated the D model, which featured a distinctive bubble canopy that greatly enhanced perceptual awareness during combat. Furthermore, The aircraft exhibited remarkable stability during flight, reacting responsively to pilot inputs, and maintaining superb performance even at high altitudes. The Merlin engine, a robust and reliable power plant, delivered smooth and consistent thrust across the aircraft's entire operational range, instilling confidence in pilots during demanding missions. Perhaps most notably, the Mustang's range and endurance were extraordinary for a single-engine fighter. Fully fueled internally and equipped with auxiliary drop tanks, the aircraft could stay airborne for more than 6 hours, an endurance capacity that rendered many German single-engine fighters, even those equipped with external tanks, unable to match. The technical insights gleaned at the Rechlin factory, also known as Rechlin, proved invaluable to German tactical development in the closing phase of the war. Understanding these aircraft's capabilities allowed German strategists to refine their defensive tactics and anticipate the threat posed by enemy fighters. By mid-1944, the German Luftwaffe's attempts to counter American aerial superiority involved concentrating fighter units at specific points with the aim of achieving local dominance, especially over bomber streams. This tactic required meticulous coordination and precise timing because German fighters, often dispersed across vast areas, had to converge at predetermined locations to form sufficiently large and cohesive formations in hopes of challenging the heavily protected bombers. However, numerous obstacles hindered these efforts. Limited fuel reserves and communications issues frequently prevented successful concentration of forces. Even when German fighters managed to find and occupy advantageous positions, the presence of well-escorted P-51 formations rendered attacks costly, plunging fighters into perilous encounters that often resulted in heavy losses. The tactical landscape had radically shifted, transforming what previously might have been feasible attempts into almost impossible endeavors. By the year 1943, bomber formations flying without escort or with inadequate escort services experienced devastating losses against Allied fighters and their superior air tactics. As the year moved into 1944, German fighters undertaking daring interceptions of well-defended bomber streams encountered catastrophic attrition rates. The loss of fighters in these battles became a grim reality, illustrating the deteriorating strength of German tactical capabilities. After the war concluded, the drop tanks used by the P-51 Mustangs became rare and collectible artifacts. Most of these tanks did not survive intact due to their fragility. Many were destroyed upon impact, while others were deliberately crushed by Allied ground crews to prevent reuse or rescue by enemy forces. Their inherent disposable nature rendered them relatively insignificant at the time, which accounted for the scarcity of preserved specimens. Those tanks that did survive transitioned into museum exhibits and historical curiosities, treasured for their connections to key wartime aircraft. The National Air and Space Museum, located in Washington, D.C., proudly displays several specimens of these drop tanks alongside the P-51 Mustangs they were designed to complement. Informative placards accompanying the exhibits detail that these tanks were constructed from laminated craft paper impregnated with phenolic resin, manufactured by companies such as Bowater Scott, with a capacity of approximately 108 U.S. gallons. Interestingly, official museum descriptions tend not to emphasize that German engineers dedicated weeks to analyzing these tanks in detail, studying their construction, materials, and capacity, uncovering through these examinations insights into the extent of Allied industrial capability and logistical planning. This meticulous scrutiny reflected a broader German effort to understand and anticipate Allied technological and manufacturing strengths, which ultimately underscored the remarkable industrial disparity that the Allies maintained throughout the war. World War II are vividly illustrated by the story of the paper drop tank, a seemingly simple piece of military technology that carried profound psychological and strategic implications. The narratives preserved in detailed military reports and post-war interviews reveal that the impact on German technical personnel was far more significant than one might initially assume. While that humble fuel tank was not a marvel of advanced engineering, nor did it incorporate cutting-edge technological breakthroughs, its design conveyed a powerful message. The Allies possessed an industrial capacity so vast and resource-rich that they could afford to prioritize efficiency and mass production over the sophistication of individual components. This particular simplicity was purposefully chosen, using non-critical and easily available materials such as paper, resin, and other inexpensive compounds. The decisive factor was not the technological novelty itself but what it symbolized. The fact that fuel tanks could be manufactured from paper and other relatively cheap materials underscored the Allies' unmatched ability to produce in colossal quantities. They had an abundance of paper, resin, fuel, and manufacturing capacity, resources that Germany couldn't hope to match, so their manufacturing decisions were driven not by shortages but by a clear focus on optimizing production efficiency at scale. German engineers and technical officers quickly grasped the significance of this strategic choice. Their immediate perception was that they were facing an adversary who was not relying on rudimentary improvisations or temporary substitutes brought about by material shortages. Instead, they recognized that the vast reserves of resources available to the Allies permitted them to make deliberate and calculated choices aimed at maximizing production efficiency. This realization was a disturbing indicator of the Allied economic and industrial dominance, a difference that, in the eyes of German military staff, portended inevitable defeat. Consultations with Luftwaffe personnel confirmed a recurring theme. By the early months of spring in the year preceding Germany's surrender, many of Germany's most experienced technical staff and senior military officers regarded this awakening to Allied resource abundance as a turning point in their strategic outlook. They understood that this level of industrial capacity had shifted the war's dynamics permanently. One of the pivotal moments in the strategic shift was the deployment of long-range fighter escorts over Berlin, which dramatically altered the aerial battlefield. The presence of these fighters marked a significant turning point, signifying a drastic change in the balance of air power. Hermann Göring, the senior Luftwaffe commander, after the war, acknowledged that the introduction of long-range escorts inflicted a severe blow to German defenses and was among the crucial reasons for Germany's ultimate downfall in the air war. This event symbolized a strategic shift. The Allies' ability to project sustained air operations deep into enemy territory was fundamentally enabled by their technological and industrial prowess. Though the specific claim regarding Mustangs flying over Berlin remains unverified in original primary sources, Göring's post-war admissions consistently recognized that Allied air superiority, achieved largely through the deployment of strategic long-range escort fighters, played an instrumental role in Germany's defeat. The technical lessons learned from examining captured P-51 Mustangs and their distinctive drop tanks were studied extensively. German engineers, many of whom later emigrated to the United States or collaborated with Allied intelligence efforts, gained invaluable insights into American production methods and design philosophies. This knowledge profoundly influenced post-war aviation development. The German engineers who had worked on or studied Allied aircraft adopted principles of standardization, the interchangeability of parts, and designing for ease of manufacture, concepts that would soon become a hallmark of modern aircraft design globally. Their experience with the paper drop tank and the innovative manufacturing approaches that it represented served as a case study demonstrating how wartime resource optimization combined with mass production could provide a decisive strategic advantage. Moreover, the legacy of the paper drop tank extended far beyond the immediate conflict. It became a foundational example taught in engineering schools and military staff colleges worldwide, illustrating how efficient industrial practices and resourcefulness can be decisive in wartime scenarios. The design philosophy promoted a mindset of maximizing the utilization of available resources through standardization and modular development, principles that would shape the future of aircraft manufacturing and military logistics. The P-51 Mustang, renowned for its roles during World War II, continued to serve in military arsenals well after the war's conclusion. It participated actively in the Korean War, primarily in roles such as ground attack and close air support. Its exceptional range and endurance, originally critical factors that made it an outstanding escort fighter during the air campaign, proved just as valuable in subsequent conflicts. The aircraft's long-range capabilities, crucial in the world's first significant jet-age conflict, highlighted the enduring importance of the technological and manufacturing lessons learned during World War II. Lessons rooted in resource efficiency, innovative engineering, and industrial scale. Europe had demonstrated its own strategic value in a very different operational environment compared to Korea, reaffirming the significance of certain key aircraft designs even decades later. The P-51 Mustang, in particular, continued to serve on the front lines with various air forces well into the early 1980s, underscoring the durability and excellence of its fundamental design, which had stood the test of time and evolving combat needs. Throughout the duration of the Second World War, more than 15,000 Mustangs had been manufactured, either during the conflict or immediately afterward. This prolific production established the Mustang as one of the most widely produced and iconic fighter aircraft in American military aviation history. Today, more than 100 of these legendary aircraft remain flying, carefully preserved and maintained by dedicated collectors and institutions around the globe. An aircraft in flight, often still bearing the distinctive markings of the combat units it once served in, acts as a moving tribute not only to its own technological achievements but also to the pivotal role it played in securing Allied air superiority across European skies. The historical importance of the P-51 Mustang extends far beyond its mere tactical utility. When considering the aircraft's deployment alongside its characteristic drop tanks, initially made of paper, these features symbolize much more than just wartime innovation. They serve as a profound illustration of how modern warfare is rooted in industrial capacity and manufacturing excellence. Indeed, the outcome of World War II was shaped far more decisively by the industrial might of the participating nations than by any single battlefield encounter. In essence, victory often hinged upon the ability to produce vast quantities of weapons, ammunition, aircraft, and vehicles more rapidly than they were expended in combat. This fundamental principle underwrote the industrial mobilization efforts of the United States, which achieved an unimaginable scale of wartime production, unmatched in history. Around 1943 to 1944, American factories reached a peak, churning out aircraft at rates exceeding 50,000 units annually. Concurrently, shipbuilding was yielding multiple vessels per single day, and ammunition was being produced in quantities measured in billions of rounds. Such extraordinary industrial output not only fueled American military forces but also supplied substantial amounts of equipment to Britain, the Soviet Union, and other Allied nations through the Lend-Lease program. Even with its considerable industrial infrastructure and technological prowess, Germany was unable to match the Allied nations' production capabilities. Several factors contributed to this disparity: their smaller industrial base, the strategic bombing campaigns targeting manufacturing facilities, loss of access to raw materials as territory was reclaimed by Allied forces, diversion of resources to various competing priorities, and inefficiencies in organization and logistics. Most fundamentally, however, Germany faced a coalition whose combined industrial capacity was vastly larger, several times greater, than its own. The influx of American industrial strength into the Allied camp, particularly from 1942 through 1943, rendered Axis defeat all but inevitable once the full scope of industrial mobilization was realized. The paper-drop tanks, scattered across German territory during the late 1940s, serve as stark, simple symbols of this industrial reality. Their presence visually embodied how technological and material superiority translated into warfare outcomes. These disposable tanks, falling in relentless swarms over Germany, made clear that the Allies' industrial preponderance had tipped the scales decisively. Throughout the war, systematic and professional efforts by German technical intelligence services included meticulous analysis of captured American equipment. Organizations like Recon meticulously documented performance test results, examined materials, and evaluated technical specifications. Many of these detailed reports survived the war, stored securely within archives, and now offer valuable insights into how each side perceived the technological capabilities of their adversaries. German evaluations of American equipment were generally accurate in technical terms, correctly identifying strengths and weaknesses. They obtained a clear understanding of the performance characteristics of aircraft such as the P-51 Mustang and other technological innovations that had a profound impact on the course of the conflict. These assessments highlight the high level of technical understanding that German engineers and intelligence analysts had of Allied machinery, an understanding that, even despite their shortcomings, reflected a recognition of American industrial and technological superiority on the battlefield. During the Second World War, the strengths and weaknesses of American aircraft, vehicles, and weaponry became a focal point of strategic analysis, particularly from the German perspective. What German military intelligence failed to grasp entirely wasn't just the capabilities of individual items, such as fighters, bombers, or tanks, but rather the unprecedented scale of American industrial production and the profound strategic implications of this industrial prowess. It became clear that the sheer volume of American goods produced, combined with their rapid manufacturing rates, fundamentally altered the balance of power in the conflict. Take, for example, the iconic P-51 Mustang, a versatile and highly effective fighter aircraft. In isolation, one P-51 was an outstanding piece of aviation technology, offering excellent agility, range, and combat effectiveness. However, when considering 10,000 P-51 Mustangs, an enormous fleet, this immense force represented a level of air superiority that no amount of tactical skill or any single technological advantage could effectively counter. It was the scale, the relentless mass production of such aircraft, that created an insurmountable advantage. This reality was vividly illustrated in March of 1944, when German engineers investigated paper-drop tanks at Recon. These tanks, though simple and lightweight, were revolutionary because they extended the range of American fighters significantly, allowing them to escort bombers deep into enemy territory. Their examination ultimately highlighted an essential truth about the nature of modern warfare among highly industrialized nations. Production capacity was as vital as battlefield strategy. A nation that could produce more, in terms of aircraft, tanks, weapons, and supporting equipment, could sustain prolonged campaigns, outlast opponents, and continuously reinforce its forces, regardless of tactical setbacks. This understanding became increasingly crucial as Germany and Japan suffered heavy losses during the war. The ability to manufacture vast quantities of advanced weapons and sustain supply lines under intense pressure often determined the eventual outcome of campaigns. Rapid training of personnel, efficient logistics, and robust industrial infrastructure allowed the Allies and their Axis adversaries to outproduce each other, but ultimately, there was a strategic advantage to the side that could generate higher quantities of military hardware over extended periods without interruption. The significance of industrial capacity was brought into sharp relief during the pivotal operations of May 1944, when American bombers began conducting missions escorted by fighters all the way to Berlin. These missions marked a turning point in the air war over Europe, as it became possible to strike targets deep within Germany with fighter protection en route. For the first time, no German objective was beyond reach for American bomber fleets, thanks to the long-range capability of their fighter escorts. Consequently, the systematic Allied bombing campaign could be carried out with a level of relative sustainability, despite losses. The strategic aim to cripple Germany's war-making capacity gained momentum as crucial industrial sites, like synthetic fuel plants, ball-bearing factories, aircraft manufacturing facilities, and vital transportation arteries, became frequent targets. Repeated assaults on these critical infrastructure points, conducted with ongoing fighter escort, exerted relentless pressure on German war production. This expansive campaign, combined with the eastern push of Soviet forces and the advances from Western and Southern Allied fronts, significantly hastened Germany's collapse. Within approximately 14 months of the first P-51 Mustangs reaching Berlin, Nazi Germany faced unequivocal defeat. Their war effort was increasingly hamstrung as Allied operations systematically eroded their industrial capacity, making sustained war effort impossible. Throughout this final phase of the conflict, paper-drop tanks remained a critical component. Produced throughout 1945 in thousands each month, these tanks not only extended the operational reach of American fighters but were also adopted widely by other Allied aircraft. The P-47 Thunderbolt and P-38 Lightning benefited greatly from these extensions of range, enabling prolonged escort and interdiction missions deep into occupied territories and enemy-held regions. Even the Royal Air Force utilized paper tanks extensively on their own Mustangs during long-range sorties over Europe and Germany, illustrating how this simple yet innovative solution became a standard across Allied air forces. The production and utilization of paper-drop tanks exemplified a broader industrial approach that prioritized efficiency and resourcefulness. By manufacturing tanks from lightweight paper, aluminum and steel could be conserved for other essential purposes, such as aircraft frames or armament, thereby optimizing overall material use. This strategic shift toward resource efficiency, matching production methods to operational needs while breaking from tradition, embodied the industrial mindset that characterized Allied military operations from the early stages through the final victory. Historians specializing in the air war over Europe now recognize that this combination of industrial capacity, technological innovation, and strategic planning was responsible for shaping the final phases of the conflict. Multiple interconnected factors, ranging from the ability to produce vast numbers of fighters and bombers to the logistical innovations like paper-drop tanks, collectively contributed to the Allied victory. Central to this tactical evolution was the understanding that in modern warfare, victory often goes to the side that can sustain continuous and effective production at a scale that opponents, no matter how tactically skilled, cannot match. from a combination of factors that extended far beyond the simple use of paper drop tanks. These additional elements included the significant numerical advantage enjoyed by the Allied forces in terms of both aircraft and trained pilots, technological innovations in critical areas such as radar and secure communications, and the relentless strategic bombing campaigns aimed at crippling German industrial capacity and infrastructure. Over time, the cumulative effect of a sustained and coordinated combat effort was to drain German resources at a rate faster than they could be replenished, gradually shifting the balance of power in favor of the Allies and paving the way for ultimate victory. While the paper drop tank, with its humble construction from lightweight paper and temporary use, was a noteworthy part of this diverse and complex campaign, mainly because it symbolized the broader industrial strengths of the Allies, it was by no means the sole deciding factor. Achieving victory over the Axis powers required a harmonized interplay among various elements, a myriad of fighter aircraft types, the formidable bomber fleets, the industrial output and technological innovations that kept these forces supplied and effective, the rigorous training programs that prepared skilled pilots, the intricate intelligence networks providing critical insights, tactical adaptations on the battlefield, and a sustained commitment of resources over many years. The paper drop tank holds special symbolic significance within this broader narrative, as it creatively exemplifies the crucial role played by industrial ingenuity in wartime success. The detailed technical records maintained at RCIN, an institution dedicated to cataloging this information, serve as testament to the tremendous capabilities of American manufacturing and engineering. These files meticulously documented everything from specifications, performance data, and manufacturing techniques, to the projected production volumes, reflecting a professional approach characteristic of American technical proficiency. These detailed archives, now preserved and accessible through various repositories including the Bunds Archive, offer modern historians a rare window into how German engineers and strategists viewed Allied equipment during the conflict. When we examine these documents today, with the benefit of a historical perspective and access to a wealth of American records, it becomes evident that German technical assessments were remarkably accurate. They correctly understood the extent of American industrial strength and technological capabilities, recognizing that the Allies possessed overwhelming advantages in both quality and quantity. However, while the Germans could analyze and assess these advantages with precision, they were ultimately powerless to alter the overarching strategic dynamics rooted in fundamental disparities of industrial capacity and resource availability. Recognizing an adversary's superiority in these core areas does not confer the ability to bridge those gaps or negate their impact. Instead, it underscores that victory depends on leveraging one's own strengths and innovating within existing constraints. The legacy of the paper drop tank extends well beyond its immediate wartime application. It stands as a powerful reminder that solutions need not be overly complex or technologically sophisticated to be effective. Rather, they should be fit for purpose. The paper drop tank, constructed from inexpensive, non-critical materials, was an elegant response to a specific operational challenge, extending the range of fighter aircraft when more durable or costly solutions might have been impractical or unavailable. Its design demonstrated that even a simple, disposable device could fulfill its mission efficiently and reliably. This principle, that solutions should be adequate for their intended purpose without unnecessary complexity, has become a cornerstone in the philosophy of modern systems engineering. It teaches that the optimal solution is not always the most elaborate or technologically advanced, but rather the one that can be manufactured quickly, economically, and in the required quantities within the available time frame and resource constraints. The story of the paper drop tanks, which fell across German territory during World War II, continues to serve as a pertinent example of resourcefulness and pragmatic innovation. The aircraft that carried these tanks, the legendary P-51 Mustang, embodies one of the most successful fighter aircraft designs in the history of aviation. Its innovative combination of exceptional range, high performance, operational reliability, and ease of production made it an invaluable asset during the strategic bombing campaigns over Europe. This versatility not only allowed fighters to escort bombers deep into enemy-held territory but also contributed decisively to the overall effectiveness of Allied air power. The Mustang's triumph was the result of a carefully balanced interplay among advanced aeronautical engineering, efficient manufacturing, and tactically deployed combat tactics, all driven by a philosophy that valued practicality just as much as technological innovation. In essence, the success of the Mustang and the broader strategic victory can be directly linked to the lessons learned from simple yet effective innovations like the paper drop tank. The importance of practical, purpose-built solutions tailored to specific operational needs, and the recognition that high-tech proficiency does not always require overly sophisticated or expensive means. The combination of industrial might, tactical ingenuity, and resourcefulness exemplified by the Allied air campaign remains a testament to how strategic innovation, whether through advanced technology or simple logistical ideas, can determine the outcome of large-scale conflicts. The victory of the P-51 Mustang during the European Air War was not attributed to any single technological breakthrough but was instead the product of a perfect synergy between multiple elements, each playing a crucial role in its success. Central to this achievement was the aircraft's inherently aerodynamic design, meticulously crafted by North American aviation's talented team of engineers led by Edgar Schmood. This finely tuned airframe was complemented by the powerful and dependable Merlin engine, renowned for its reliability and high performance. Additionally, the inclusion of a fuselage fuel tank extended the aircraft's range significantly, allowing fighters to operate over greater distances without refueling stops. The deployment of auxiliary drop tanks, which could be carried externally and jettisoned once empty, further amplified the operational radius, enabling entire missions to surpass 800 miles in reach. It's important to emphasize that no single component was solely responsible for the Mustang's combat superiority. Rather, its effectiveness was the result of the seamless integration of all these technological and design innovations. Furthermore, this integration was supported by a robust industrial capacity that could mass-produce these sophisticated parts and assemblies in large quantities, ensuring a steady supply for the battlefield. This collective effort, combining engineering ingenuity, strategic design, and industrial capability, transformed the P-51 into the definitive escort fighter during the critical years of the European conflict. Reflecting back, over 80 years after those pivotal battles in March of 1944, the lessons that stem from this story remain profoundly instructive. The analysis of captured German equipment at Rechlin by Wehrmacht engineers uncovered insights far beyond mere technical specifications. It provided a window into the broader strategic realities at play. The use of paper drop tanks, constructed from glued-together sheets of craft paper, demonstrated the remarkable industrial capacity of the United States, far exceeding that of Germany. These tanks illustrated that American engineering prioritized practical, functional solutions over striving for absolute technical perfection. This approach enabled the Allies to develop effective, mass-produced equipment that utilized available resources efficiently, rather than resorting to desperate or hurried substitutions, thereby maintaining a significant logistical advantage. The timing of these findings, during March of 1944, was particularly significant, as it occurred when the outcome of the war was still far from decided. The Germans' technical staff gained a clearer understanding of the immense challenges they faced, acknowledging the breadth of American industrial strength, resourcefulness, and strategic foresight. Yet, this knowledge, impressive as it was, could not alter the final course of the conflict. The defeat of Germany had already been sealed by countless factors largely beyond the control of the engineers working in isolated laboratories and testing facilities. However, the detailed examination of the paper cylinders, their capacities, and their role in the air campaign offers valuable insight into a fundamental truth of modern warfare. That industrial capacity, harnessed through strategic innovation, often determines victory more decisively than raw combat prowess alone. By the end of the war in May of 1945, the Allied forces had achieved a decisive upper hand. The extensive bombing campaigns, made more effective by long-range fighters like the Mustang equipped with drop tanks, some ingeniously crafted from paper, significantly contributed to the collapse of Nazi Germany. The destruction of transportation networks, the crippling of industrial infrastructure, and shortages of fuel all played parts in weakening the German war effort. The Luftwaffe was effectively relegated to a symbolic force, incapable of mounting sustained, effective offensive operations. Although multiple factors, operating over many operational years, drove these outcomes, the critical ability of fighters like the P-51 to escort unprotected bomber formations deep into German territory proved a decisive element. Their long-range capability, facilitated by drop tanks, including those constructed from paper, allowed Allied strategic bombing to be lethal and persistent. Many of these paper drop tanks, once their service was complete, became silent witnesses to a pivotal chapter in history. While only a select few are now preserved in museums, the majority were deliberately destroyed or discarded even before the end of the war. Their true significance, however, transcends their physical form. These tanks symbolize a broader story: the incredible reach of industrial capacity when directed with strategic intent, the innovative application of technology tailored to specific military needs, and most notably, the overwhelming advantage gained through sheer production capacity. This narrative, underpinned by technical reports from Rechlin and other archival sources, continues to shape our understanding of not only World War II but also the fundamental nature of modern industrial warfare. In essence, the story of the paper drop tanks exemplifies how technological ingenuity, strategic resource allocation, and industrial scale can combine to determine the outcome of some of history's most consequential conflicts.